Hello class, I am Happy Narang, your subject teacher of Fundamentals of Soil Science. Today I am going to cover the topic that is ion exchange and its role on soil behavior. So let's start. Soil colloids will attract and hold positively charged ions to their surface replacement of one ion for another from solution that is called cation exchange. For every cation that is adsorbed, one goes back into soil solution. Now we'll talk about cation exchange capacity, and in short we can say CEC. In soil science, the maximum quantity of total cations of any class that a soil is capable of holding at a given pH value available for exchange with the soil solution. Here we will understand why do soils have CEC. The cation exchange capacity of the soil is determined by the amount of clay and humus that is present. Clay and humus, cation warehouse or reservoir of the soil. Sandy soils with very little OM represent organic matter. Low CEC. Clay soils with high levels of organic matter, much greater capacity to hold cations. Negative soil particles attract the positive cations. Sand Si2O4, no charge, doesn't retain cations. Clay SiAlO4 minus, negative charge, attracts and retains cations. Why do clays have CEC? If the mineral was pure silica and oxygen, the particle would not have any charge as shown in the figure. Isomorphous substitution. However, clay minerals should contain aluminium as well as silica. They have a net negative charge because of the substitution of silica by aluminium. In the clay, this replacement of silica by aluminium in the clay minerals structure is called isomorphous substitution, and the result is clays with negative surface charge, tetrahedron, octahedron as shown in the figure. How these are forming basically sharing of O or OH group sheets and unit layers, tetrahedral sheet and octahedral sheet. How the sheets are forming you can observe by this figure. Clay unit structure are shown in the figure. Now the clay type minerals mostly kaolinite, SiAl, hydrogen bonding between layers. This gives type mineral a very rigid structure, well crystallized, low cation adsorption, little isomorphous substitution, larger particle size, that is 0.1 to 5 mm, fixed lattice type, no interlayer activity, no shrink swell, only external surface. You can observe by this figure. Type minerals expanding lattice, smectite group, mostly morillinite, freely expanding, water interlayer, large shrink swell, small size, poorly crystallized, large internal surface, isomorphous substitution, large cation adsorption, adsorbed cation in interlayer. Expanding clays are shown in the figure. Non-expanding lattice, fine grain micas or elite. Some distribution of air for Si in the tetrahedral layers leads to permanent net negative charge. Al plus 3 and Kl plus substitute for Si plus 4 tetrahedral sheet. Weathering at edges is equal to release of K plus, very limited expansion, medium cation adsorption, limited internal surface, properties between kaolinite and vermiculate, non-expanding clays are shown in the figure. Chlorides, Mg replace K plus of light, similar to elite. Vermiculate similar to smectite, more structured, limited expansion, rather large cation adsorption. Clay comparisons are shown in the figure. Structure of clays. This table shows the summary of properties. This figure shows what actually happens in soil. You can observe it by this figure. Here is the conclusion. From the previous discussion, it is obvious that the amount and type of clay in the soil determines cation exchange capacity. In addition, the type of clay also affects cation exchange capacity. There are three types of aluminosilicate clays in temperate region soils: known clays, kaolinite, elite, montmorillonite, CAC, shrinkage and swelling. You can observe by this figure. How tighten iron is held. Iron's hydrated radius, smaller radius is equal to tighter hold. Magnitude of ion charge, higher charge is equal to tighter hold. Al3 is greater than Ca2 plus. Ca2 is greater than Mg2 plus. Mg2 is greater than K plus. NH4. NH4 is greater than Na plus. Na plus is greater than Li plus. How likely an ion species is to be adsorbed is determined by its concentration in the soil solution. Higher concentration is equal to more adsorption. High concentration of one ion species relative to another ion species can supersede the effect of radius and charge. In chapter 3, we will discuss the surface properties, or we can say surface properties relations. There are some important correlations between some surface properties of soil that have to be obvious. These properties are clay fracture content, clay mineral type, specific surface area, and cation exchange capacity. Total surface area of different clays. According to this chart, it is expected to cation exchange capacity have an increasing trend from montmorillonite to kaolinite. Surface area of clays are shown in the figure. In chapter 4, we will discussing about engineering properties, how the surface properties affect soil physical properties. So let's start. Many properties of the fine-grained soils are attributed to cation exchange, which is a surface phenomenon. By replacing the existing cations in the exchange complex, several improvements can be effected in the soil properties. These beneficial changes are in the form of reduction in plasticity, increases in the strength, and reduction in the compressibility. Lime stabilization are shown in the figure. The addition of lime to a soil supplies an excess of calcium ions, and cation exchange can take place with divalent calcium Ca+2 replacing all other monovalent cations. The base exchange phenomenon has been used by several investigators to explain the effects of chemical stabilization. K. Matthew, 1997. Following previous sessions, some soil engineering properties changes that found to be related directly or not with cation exchange process are discussed. Atterberg limits, dispersion, hydraulic conductivity, swelling potential, compressibility, consolidation. These all are soil engineering properties as shown in the diagram. Atterberg limits Sridharan et al. 1975 tested 7 natural soil containing montmorillonite as the dominant clay mineral and showed the relationship between the Atterberg limits and clay fraction CF, SSA and CEC. The liquid limit versus CEC shows somewhat of a linear trend as indicated in the figure. CEC versus LL percentage, Sridharan et al. 1975 are shown in this figure. Shrinkage limit. The shrinkage of clay soils is often said to depend not only on the amount of clay but also on its nature. Green Calais 1974. Montmorillonite soils is equal to high water adsorption is equal to high shrinkage. Optimum clay content, Sridharan 1998, 30 and 50%, and we can observe by this figure. Dispersion. Surface area may also play a significant role in controlling the behavior of dispersive clays through surface charge properties. For an example, Cation et al. 1977, Hamsi et al. 1988, Sridharan et al. 1992, Bell et al. 1994. Sodic soils are typically highly dispersive. Sodic soils have a high concentration of exchangeable sodium plus, therefore much of the negative charge on the clay is neutralized by Na+, creating a thick layer of positive charge that may prevent clay particles from fluctuating as shown in the figure. Hydraulic conductivity. A laboratory study of the hydraulic conductivity, in short we can say HC, of a marine clay with monovalent, divalent and trivalent cations revealed large differences in hydraulic conductivity. Rao et al. 1995 suggests that hydraulic conductivity is significantly affected by the valency and size of adsorbed cations. An increase in the valency of the adsorbed cations for a constant valency, higher hydraulic conductivity. An increase in the hydrated radius of the adsorbed cation is lower hydraulic conductivity. As per Ahmad et al. 1969 and Kirik and Schofield 1955, hydraulic conductivity is related to exchangeable cations in the following order: calcium is equal to magnesium is greater than potash is greater than sodium. Now we'll talk about the swelling potential. The more montmorillonate in the mixture, the more internal surface and the surface area. As the surface area increases, the swelling potential increases. D. Brain et al. 1957 percentage results and a classification of various soils using specific surface area and moisture contents. His criteria state that soil with TSSA is less than 70 meters square per gram and W percentage is less than 3%, non-expensive, obviously good. TSSA is greater than 300 meters square per gram and W percentage is greater than 10% is expensive, so it is bad. Now comes compressibility. It has been established that the thickness of the double layer is sensitive to changes in cations present on the surface. Van Olfen 1963. The divalent and trivalent cations in the adsorbed complex of clay soil are known to reduce the thickness of the diffuse double layer by 1/2 and 1/3 respectively. Michel 1976. At increase in valency leads to a reduction in compressibility, and at a constant valency an increase in the hydrated radii of the adsorbed cations resulted in an increase in compressibility. Further, it has been found that per consolidation pressure increases with valency of the cations. K. Matthew 1997. Thank you. Stay home, stay safe.